Our last topic is looking at how manipulating a reaction affects the equilibrium constant. And this is something that you could do without me giving you all of these rules. Um, but I'm going to give you proof for each one so that it will help you remember the rule and hopefully, if nothing else, remind you of why if it's on the left, we call it a reactant. If it's on the right, we call it a product. And we don't change the reaction. We don't flip it. Or if we flip it, then we're going to have to change the equilibrium constant, right? Because the equilibrium constant is tied to the temperature and the reaction in the way that it is written. So let's do some manipulations. First manipulation, what if we reverse the reaction? Well, if you reverse the reaction, you have to invert the KEQ. And by have to, I mean, if you would like to reverse the reaction for literally any reason, you can do so. And you can calculate your new KEQ by inverting the given KEQ. Right? So not just a have to, but a can. If you would like your reaction reversed, you can do it. You got to change your KEQ. All right, proof. If I have the reaction A plus 2B in equilibrium with 3C, my equilibrium constant expression is concentration of C cubed over concentration of A times concentration of B squared. Versus if I flip or reverse my reaction, so 3C in equilibrium with A plus 2B, and I write my equilibrium constant expression, it's concentration of A, concentration of B squared over concentration of C cubed. The expression on the left related to the expression on the right, they are inverse of each other. Okay. Second manipulation. If I multiply a reaction by a number, then the equilibrium constant is raised to that power. So if I need to change the coefficients in my reaction for any reason, right, n is just some number, right? If I multiply through by 2, which we've done in balancing redox reactions, the way that I get the new equilibrium constant is if I multiplied by 2, I would square it. If I multiplied by 3, I would cube it, and so on. So we're going to do A plus 2B in equilibrium with 3C and compare it to n times A plus 2n times B in equilibrium with 3n times C. So I've got my generic multiplier in here. Equilibrium constant expression on the left, same as above, C cubed over A times B squared. On the right, it's concentration of C to the 3n over concentration of A to the n, concentration of B to the 2n. If you factor out the to the power of n, the result is the equilibrium constant, right, C cubed over A times B squared, all to the n power, which is why you can just take the value of the equilibrium constant and take it to the n power. The last manipulation is that if we add reactions together, which we have done before, we'll definitely do it again, you multiply the KEQs. So we're looking at A in equilibrium with 2B added to 2B in equilibrium with 3C. So if I write the equilibrium constant expressions for these individually, so I've got one marked in purple, one marked in blue. The A in equilibrium with 2B, my expression is B squared over A. 2B in equilibrium with 3C, my expression is C cubed over B squared. If I add these reactions together, right, on the left I have A plus 2B in equilibrium with 2B plus 3C. My 2B's cancel out. So I have A in equilibrium with 3C. If I take the bottom, my resulting reaction, and just write the equilibrium constant expression, I get concentration of C cubed over concentration of A. So I should get that exact same result if I multiply the equilibrium constant expressions from the individual reactions. So I want to take b squared over a, multiply it by c cubed over b squared. And if I do this, my b squareds cancel out. So I end up with c cubed over a, which matches what I got when I wrote it from the resulting reaction. So if you add reactions together, you can get the new equilibrium constant by multiplying the KEQ values. So as an example, the way that you are going to see this is that we have a reaction NH3 in equilibrium with half of an N2 and 3/2 of an H2. And we want to know the equilibrium constant for that. But what we know is that the equilibrium constant for N2 plus 3H2 in equilibrium with 2NH3 is 5.6 times 10 to the fifth. So these have the same molecules in them. Now the products don't match, the coefficients don't match, the reactants don't match. Like we have to do something, but it has the same things in it. So if you can figure out how to get from the original reaction to the target or the unknown reaction, then you will know what to do to the equilibrium constant value to find the new equilibrium constant. So, I mean, one, my NH3 is on opposite sides for these two. So one of the things to go from the original to the target is that the reaction had to be reversed. So if I reverse the reaction and I have 2NH3 in equilibrium with N2 plus 3H2, the equilibrium constant for this will be the inverse of the original. So my KEQ is 1 over 5.6 times 10 to the fifth. And now I haven't bothered multiplying this out. I'm just going to carry that forward as my new equilibrium constant because I've got to do more. I'm still not at my target reaction. And then, I mean, it goes down to 1 NH3. So it looks like it was divided by 2. Yeah, because that would give us 1 NH3, 1/2 N2, and 3/2 H2. So we divided by 2. We didn't have a rule for division, but dividing by 2 is the same as multiplying by 1/2. So if I multiply by 1/2, I have to take the equilibrium constant to the 1/2 power. So the new value of my equilibrium constant is the square root of 1 over the original equilibrium constant. So my final value is that the equilibrium constant for the unknown reaction is 1.3 times 10 to the minus third.